let's look at an example and then go into the exercises in 6b. A weightless seesaw, because these things do exist, is at rest with a boy of mass m sitting at the lower end at ground level. There's my seesaw. There's my stanchion holding it in place. It's a great diagram. Needs a bit of support. So I have a boy here at ground level, and then obviously it's going to go down and end up at ground level over here. So the height at this point will be 0. So we definitely have potential energy and kinetic energy going on here. There's a boy here. He has a mass of m. His dad is up here. He's 3 times heavier. He is 3m. And that's the only information we're given. And we're looking for the speed just as the father hits the ground. So literally at just this point here where h is equal to 0 over the far side. That's what we're to assume. So let's look at the energy in the system before and after. So there's 2 people involved here. So there's mgh for the boy here plus a half mv squared. And there's mgh here for the dad and also a half mv squared. So there's going to be a lot of zeros involved here. This is mg by 0 and he's not moving, so it's a half m by 0 squared. Up here we have mg, and what were we told height was? I should have put it in. The height above the ground is 1 meter. I couldn't find it. 1 meter above the ground, so this is a 1. So mg by 1, and it's at rest, so he's not moving. Half m v squared. Just putting his mass in 3m, we have 3m times g, and the velocity is 0 is a half times 3m times 0. So the total energy in this system is 3mg. These are all zeros. Okay, so what's happening afterwards? Just as it's about to hit the ground, let's do another diagram. Just maybe keep that there. So just do a smaller diagram here. So now my seesaw is the other way around. So the boy is up in the air and the dad's on the ground. Height again is 1. We have m up here and 3m down here, and we're looking for speed. So let's look at the energy. We have a half mv squared, which we don't know v, plus mgh, which is mg times 1. Down here we have a half we don't know v squared, but sorry, I just put my 3m in, a half 3m. Let me tidy that up. A half m equals 3m here, just be careful. It's an easy mistake not to put 3m in. A half 3m by v squared plus m, which is 3m by g by 0, which is the height. So this one's the 0 in this case. So we have a half mv squared plus mg plus this one here, which is going to simplify down to 3 over 2 mv squared. 3 over 2 mv squared, or 1.5 mv squared. So my initial energy, 3mg, has to be equal to these guys. 3mg is equal to mg, this one, and we got 1.5 mv squared plus a half mv squared, so we've 2 mv squared. So I get 2 mg, bringing mg to the left, is equal to 2m v squared, and dividing across by 2m, I get v squared is equal to g, so v is equal to the square root of g, which is approximately 3.13 meters per second. Question 1, a projectile fired from level ground, same as one of the previous videos. So what's going on here? We have position 1, position 2. Let's look at position 1, mgh plus a half mv squared for position 1. Position 2, my wife just barreled into the room. We're going to apply mgh plus a half mv squared to position 2 too, and they're going to have to be equal. So in position 1, we have my v is 20 and my height is 0. V equals 20 and h equals 0, or put what we need here. So we have mg times 0 plus a half m by 20 squared. 20 squared is 400, so that's going to give me half 400, 200 m. So this has to be equal to, what's going on here? Well, we're looking for speed. We do have height, so this is going to put a 10 in here, 10 meters above the ground. So we have mg by 10 plus a half mv squared equals the 200 m below. So I have, convert my g, 10, 9.898 m plus a half mv squared. You get rid of your m when you want, is equal to 200 m. So I'm going to get v squared over 2, so just v squared is equal to 200 minus 98, 102, and then times the 2 that was on the bottom. V squared is equal to 204, so v is equal to the square root of 204. V is equal to 14.28 meters per second. Question 2, we're given a particle of mass m swings at the end of a light string. So here's my string and I have a particle at the end of it. It's the same question as the swing question, just we're dealing with a particle at the end of a string, and we can actually take this position here. We can take this as height equals 0 at this point. So it's going to swing up here and it's going to reach this height up here above this position, height equals 0. So the speed is 2 at the lowest point. So let's look at this as position 1. So position 1, mgh plus a half mv squared is m times g times 0 plus a half times m times v squared, and we're told v is 2, so that's 4. So that's just going to be 2m. So that has to be equal to the energy at position 2. So again, we have mgh is what we're looking for, plus a half mv squared. And you all know that at this position of greatest height, the velocity changes to 0 before it comes back down. So we're just going to have mgh plus 0. So therefore 2m is equal to mgh. Cancelling my m's, I get h is equal to g. Now h is equal to 2 over g, which is equal to 2 over 9.8. And typing this into a calculator, are we looking for it in centimeters? H is equal to, in meters, 0.204, 0.204, so that's 20 centimeters to the nearest centimeter.